This is a talk that I've given once before in San Francisco, so you might have seen it online. There's been some tweaks and things, because back then it was Erlang 19 was about to be released, was it 3 months in the future? Now it's been out for 3 months. So it's about the same talk, only with that perspective in mind. So yes, so I'm going to go through kind of an overview of what tracing is, what the different capabilities that the virtual machine exposes to you, so what you can do and all of the different things, just to give you an idea of what is possible to do with Erlang tracing today, to the things. The different ways that you do introspection inside to gather information inside the virtual machine. And then I'm going to talk about the work that I did during winter this year to make the tracing better, faster, more scalable, and easier to use, more flexible. And talk a bit about my ideas and things that I want to do in the future with tracing. So tracing is kind of a way of doing some kind of dynamic logging in the system. So you have a problem that you haven't foreseen is going to happen, and you want to figure something out in the system, that you want to know why a certain thing is behaving the way it is, and you didn't put a logger statement saying that you want to log this specific path of code in part of the code into a file or something like that. So you put on tracing to do that. In Erlang, it's built into the virtual machine. You can trace on basically all different kinds of events that you could think of. You can trace on function calls, you can trace on message passing, you can trace on process states, you can trace on what's happening with the garbage collector, you can trace with scheduling ideas, you can trace to see how long different kinds of garbage collection or scheduling events takes. There's a lot of different things that you can trace on, and it's the main way of introspecting and looking at what's happening in your systems. When you're tracing, the normal ways to do it is that you either trace to a file that you then read somewhere else, or you trace to some IP port, you send it over TCP, or you trace just to standard out and read it in your console. The basic way to get started with tracing is that I use DBG. I love DBG. So DBG, just you start your tracer, you trace on all the different processes, then you say you want to trace on a module, the lists module, the sequence function, and you want to do exception tracing, and then you call the function and you see what happens. Very simple to get started, and then you get exactly what's happening in your system, and you can build on this and make very complex traces and get exactly the information that you're looking for. In a system, we have a bunch of trace receivers, so different ways to what happens with the data that when you're tracing. So you have two choices in the current, before 19, you had two choices. You could either send the traces to a process, and that process could decide what to do with the trace message. For instance, it could print it to standard out, so the normal tracer that just dumps everything to the terminal, that's a process trace, so it receives a trace message of some sort, formats it in a nicer way, and then puts it out into the console. Or you can do some kind of analysis in real time of these things. So you can say that, okay, so if I receive this trace message followed by this trace message followed by this trace message, then I want to do some kind of printing to standard out in order to filter so that you don't get so many messages printed out to your console. I believe this is like tools like Redbug and Recon uses this in order to don't overflow your system. So they have some kind of state in that process there. Or you can send it directly to an Erlang port. So you have two different ways of sending them. And the ways that the ports that are shipped with the with runtime tools, with the Erlang OTP, is that you can either trace to a file or you can trace to a TCP socket. And then all the data gets flowed either to a TCP socket or to a file on disk. And then you can do with that data what you want. So trace events, so there's a bunch of different trace events that can be generated. So in a small example code like this spawn fun here, there's a bunch of different trace events that are happening that you can trace on. So the first thing that will happen here is that you will be scheduled in. So when the message is sent go to this thing here, it will get a receive trace saying, I received this message. So you can trace on saying received. When it gets received, you also get a scheduled in because this process gets activated, so you know that this gets scheduled in, and you can get timestamps associated with it. And then you can get a call seeing that, oh, there's a function call happening to this function, and there's a return from that function, so you can measure the time that that function call took, for instance. And then you get a schedule out. So now you have an in and out event. So you can, for instance, do a trace saying, okay, so how long runtime does this process had when it was running? Why, and do analysis of this. And then it went into a receive after. So we're waiting for a timeout. And we get a schedule in, and then we get a timeout event that we can also trace on and see that that happened. And then that the process exited, so we get a final event saying that the process exited, and then the process actually terminates. So there's a bunch of different things, and we can track the life cycle of the process using these kinds of different tracing probes. When tracing, we're talking about both code and live processes. So when you're tracing, you normally set up a trace saying that, okay, the intersection of the processes that I'm interested in together with the code that I'm interested in, that's what I want to know. So if I only want to trace on a certain few processes within one supervision hierarchy, I can say, okay, I want to trace on these processes, and whenever they call this code, I want to get a trace message. So you're always working with the intersection of the two. So you're working with processes and the code working in there. Obviously, for like send tracing and receive tracing, you only have the entity that you're working with because there's really no code involved. But when you're working with the code, you're working with the intersection of the different two. And you can also configure it so that each process has its own trace receiver. So it's not like you have a global trace receiver for the entire system. It's each process that has its local trace receiver. So you can have a certain supervision hierarchy saying, okay, I want all my trace message being sent to this process. And then some other processes, I want it to be sent to another port or something like that. So it's divided between the different parallel entities within the virtual machine. So that's the basics that you use. So now we're going to get into the more advanced stuff and the features that we have in the virtual machine. So there's this thing called meta tracing, which is tracing if you just disregard the processes. So you're just tracing on code and code calls. You're saying all of the different, all the processes when that code is executed, this meta tracer is run. And some code. So you start it as normal. And you say that when you set up your Erlang trace pattern, so this is using like the low-level trace BIFs, we say that, okay, so when genserver cast with the arity of 2 is being called, I want a meta trace message to be generated. So now I don't have to enable saying what kind of, which processes. So for all processes running in system, this will be true. And now I have a local tracer associated with this code specifically. So when I call this genserver cast, send a message to myself, I will get a trace event saying, okay, so now this genserver call cast was done, and I get this trace message, and I get a timestamp and so on. And this is kind of works in conjunction with the other tracing. Normally, with meta tracing, you try to build tools and events in order to work with the other kinds of tracing. There will be more examples of this later, I think, in the match specification part. Yes. So that's meta tracing. So tracing on code, and we first had tracing on processes and code. So match specifications is a way that we have a description language for us to kind of filter and analyze trace events as they are happening. So you can't, unfortunately, you can't write Erlang code in this part because it's executed way down into the virtual machine, and we cannot run Erlang code down there. So you have to write these match specifications that are run within this part, and it's kind of a separate language that is used for ETS and for tracing. So you can do lots of different kinds of early filtering and triggering on different events with match specifications. So you can discard events much earlier, so you don't have to deal with the load of them. or you can change the behavior of the tracing, saying that you want to all of a sudden start to trace on sending or receiving or trace on scheduling events or something like that because a function was called. So when genServerCast was called, I want to start tracing on received messages on this process or scheduling events on that process or something like that. You can do this with match specifications. A general match specification might look something like this. So there's all of this kind of unhappy sad faces, and then this specification. This is basically this code. So it's a function taking 3 arguments. The 3 arguments comes from having, there's a list with 3 elements in it. And the first one has to be a tuple with 2 elements, and then we don't care, and then we have a list. And when the length of the list is 1, we do a return trace. So we have the functional arguments, and then we have a guard clause saying what should be guarded, and then we have what's going to be happening. And in the match specifications that we use for tracing, we have an implicit message true. So this is going to generate a message for this event, and it will also apply a return trace telling it that when this function returns, I also want to get a message. So if we do something more complex or different anyway, so I can do a genServerCast here, and I only want to have trace messages when I send it to myself. So I set up a match specification saying that when the function in the match program self equals the PID of the shell in this case, that's when I want to enable tracing of send on myself with this specific tracer. So enable trace with send on myself, and enable it as a meta trace. So then when I then call genServerCast, it will execute this match specification, and it will generate a message for the meta trace, and then it will enable send tracing on that process. I will actually get also the message saying there. So from that point on, all of the messages that this processor sends will generate a trace event. So we can build algorithms and logics into this, saying that, okay, so when this function is cast, I want to change the tracing behavior of the process that called this function at this point, and do this kind of thing. So in a production system, for instance, you might say that, okay, when this function is called and the arguments to this function is blah, 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 it has this thing, this identifier I know from some customer or something like that, then I want to enable call tracing on this process for these different modules, and I want to also have send and receive tracing on this process to see what things it's interacting with. And I also might do something like set on links tracing, so that I propagate my things that's happening with this process, so that I can trace exactly what this specific customer is doing and try to track down why it's not behaving the way he thinks it should be. And you can put on a message false there, then it won't generate a message, then you will just get saying that, okay, so I'm just going to do put on a trace for sending on that process. And you can enable, disable these kinds of tracing. I find it very useful when trying to lessen the amount of trace messages and the impact tracing has on the system. So there's some other tips and tricks for this with match specifications and trying to control tracing. There's something called a trace control word that you can use, which is a global variable that you can use to control tracing. It's set to an integer. I think it's a 32-bit integer that you can just set and say, and drive the behavior depending on what that integer is set to. So and there's all kinds of math you can do in match specifications. So you can do like checking if this bit is set to that, then you're going to have this behavior. Another bit is set to that, you can do that behavior, or lots of different things. You can enable and disable tracing as you go along, as I show you, and you can also, especially when you use it in conjunction with meta tracing, normally you don't want to have messages generated for the meta tracing. So you want to have a meta trace saying, okay, I'm not going to generate a message for this, but I'm going to do the behavior of the match specification, for instance, enabling or disabling traces in different ways. So here we have another complexer example, even more, using the trace control word. So you can get the trace control word saying, okay, so I set up a trace pattern of list sequence 2 again, and I don't care about the arguments, but when the trace control word is 1, I enable tracing with send using this tracer, and I don't want a message, but when it's not sent to 1, then I disable it. So I can just go saying that, okay, so now I want to have tracing. You set the trace control word, so you can do Erlang : trace control word, and you will set it for the virtual machine, and then you will run all the processes there. You will all have send tracing on them, and then you disable it, saying, okay, so now I don't want it anymore, and then you can get a snapshot of what you're running. So, for instance, here we have a small fun running list sequence, blah, blah, blah. And if the trace control word is from the beginning, it's 0, so there's no trace generated. But when I set it to 1 and I do the same thing, so I get the message. So I can control it in different ways. So that's the crash course to match specifications. Not going to talk much more about that there. So there's another way of tracing that's called sequence tracing. I'm going to mention a bit. It allows you to follow a series of events happening in a system as messages are being sent and received within it. So say you're having something that's coming in on the edge via a TCP socket that's generating something that sends a message off to some other process, that sends a message off to another process, and then sends messages back. And then you have this chain of things. So sequence tracing is a way for you to say that, okay, this specific message, I want to trace this message and all the messages that it generates and sends back in your system so that you can follow an execution path. And you can also use this to kind of say that, okay, so when I'm following one of these sequences, I want to do call tracing on specific modules or functions along the way, so that you work your way in the system, so that you can say that, okay, I want to have this, and then it follows along in different ways. And one of the nice things about this is that it works over Erlang distribution. So you can send a kind of set, it comes in here, and then it actually goes over to another Erlang node. And then if you have tracing running there and you have a trace receiver on that side, it will continue collecting messages. You can see it in your distributed Erlang system, how it's behaving and where everything is going. And hopefully find why it's not working the way it's supposed to. And of course, yeah, sequence tracing is part of everything in tracing. So you can use mass specifications with sequence tracing to do the filtering and figuring out what you want to do and so on. So lots of flexibility there. We also have support in the virtual machine for some internal probes using dtrace and system tap. And now in Erlang 19, we also have LTT-ng in there. So you can trace on, using these kinds of system profilers, you can trace on internal emulator events and things that are happening inside, and also with the Erlang code, like some function is being called or message being sent and so on, using dtrace or system tap. So dtrace on BSD or Solaris, and then system tap on Linux, or now LTT-ng on Linux. As well. So this is kind of useful because you can use it to correlate with other parts of the system that also uses dtrace. So for instance, you can check like what the kernel is doing because you did a file write to a disk. You can see what's happening and why there are delays, or you can see what the TCP stack is doing and correlate a send over a TCP socket from your Erlang application into the kernel and see what the TCP stack is doing and why it's taking so long and which buffer it ends up in and what you should tune all the way. Quite useful. So that's the overview part of the talk. So that's all of the different tracing and instrumenting capabilities that I could think of. That's part of the virtual machine and what we do there. So as I said in the beginning, during this winter, I was working for a couple of months trying to improve tracing to make it more flexible, and especially have less overhead when you're tracing. So let's start with one of the first things that I was looking at was to try to make it scale better on multiple cores. The tracing that's before 19 didn't scale very well when you had like if you had a 16-core system all generating trace events at the same time. The performance got poor very quickly. So a brief description of what the architecture kind of looks like in before 19. So you have a bunch of processes on one side generating trace events of some sort. So calling a function, sending messages, and being scheduled in or out, garbage collection events, whatever. And all of these got put into a single queue that was protected by one single mutex. And then all of the events were ordered in that order so that you got it in the same way. And then there was another thread within the virtual machine that consumed this queue and then sent the messages to the appropriate entity, so either a port or a process that wanted to receive them on the other end. So an obvious question in this part, why didn't the processes themselves send this message immediately to the receiver? Because the processes know which receiver is going to get the message. And this is part of a implementation detail inside of the Erlang virtual machine that's called the global lock order that we use inside the virtual machine in order to guarantee that we don't get any deadlocks from our different locks or different things. So I think the next slide will talk a bit about that. Yeah, so the global lock order, the way it works is that we have around 90 different locks of different types within the virtual machine. And all of them are ordered so that we have one top lock that's the highest priority, and then we have a second, third, fourth, fifth, sixth, 90th lock. And you cannot take, if you're holding lock 2, you cannot take lock 1 without first releasing lock 2. So we have an order saying that you cannot take a lock above you without first releasing the locks that are below and then trying to take it the other way around. And the problem here was that in order to send messages, these processes, they needed to take what's called the process message queue lock, which is a very high order lock. And normally, when we're generating trace messages, we have a few of low-level, low-priority locks taken, and we don't know which locks are being done, like for scheduling events or doing something like you're inside a port, your process being called in a port. So it's very complex. So in the initial SMP implementation, the easy solution was just to say, no, we're just going to create a new lock that's very low priority and put it inside the queue of that lock, and then let another thread deal with it. So it's a common strategy to deal with these things. And there's still a few things going around there. So we have a problem here saying, okay, so we need to have this higher order lock, which is the message queue lock, but we don't know which locks we have underneath it there. So that's why we have this other process where everything is proxied via. So in 19, I did a couple of changes to this thing. So one of the things was that it turned out that the only lock that was kind of difficult, that's lower than the message queue lock, was the process status lock. And that wasn't strictly needed in most of the places. So I removed the need to take that lock. So we only had to deal with the process message queue lock. And in that case, when we generate this kind of event, we try to do a try lock on that lock. And if that succeeds, then we can just go ahead as usual, because we can circumvent the lock order by doing try locks instead of doing forceful locks. So as long as we're not waiting for a lock to be released, we can't get a deadlock. So if we only try lock it, then we can go up the hierarchy of locks. But we still have to deal with the case when the try lock fails. And spinning is not okay. So because then we could spin for infinity if we end up in a deadlock situation. So I had to introduce a per process queue of messages that is protected by a low order lock that I knew that I could take. So it's taken whenever you generate a trace message to a process, and then if some different logic. So the basic algorithm now works that, okay, we first take the process trace lock, and we check our own queue, because if we have something in the queue, we need to preserve the order of trace events. So we can't just do a try lock and try to send it. If we then have something in our queue, we might get trace messages that are out of order, which will be very confusing if the return of a call comes before the call of the function. So it's we have to preserve the order of things, and a lot of different things, like the reception of a message has to be able to correlate with the call that message actually generated when it did it, so that we can think about things. And this is a requirement we have with Erlang tracing. If you use something else, like for instance LTT-ng tracing, they don't have this. So you get ordered events that say like, okay, I called this function that should have caused this to happen, but that log entry actually ends up before it because they don't have this ordering guarantee. But we have that for the Erlang tracing, and it's very, very useful when reasoning about things. So if it's not empty, we add it to the trace queue. So we just append it at the end of the queue. We go back. If the trace queue is empty, we try to do a try lock on the message queue of the tracer. If we can, we just send it on. And this scenario here happens normally around 99% of the time. So that's the fast path that we try to do, and it almost always succeeds that we can do this. Especially if we're not on a trace-heavy system where there's not a lot of trace events happening, it's going to happen 100% of the time. If there's a bunch of tracing happening to the same trace process, we may have a problem. But then we just buffer it in our own queue and then send it on as a batch later on. And if it's busy, we add it to our own queue and then schedule the tracee for clearing of this as soon as possible later on. So instead of having this complex thing, we now just send it straight to the processes and ports at the other end. So some functional implications of this. Trace messages are more likely to be out of order for things that you think that, okay, so these things should happen after each other. Some examples, like the guarantee that we have with tracing is that trace events from a single concurrent entity should be possible to see in the same logical interval. So they are ordered. But in between different logical entities, we do not guarantee any order as such. So having a send and the receive of two different trace messages, we can't guarantee that they are in order. We can say that the send is going to happen, and then we get the receive afterwards, so that we can guarantee, but we can't guarantee the causality, so the send and then the calls within that process together with the receive on the other end. So and that was a guarantee that wasn't there before either. It's just that now it's become more likely that you can actually see these kinds of events, and especially if you don't enable timestamp on your traces, you won't see a difference. But if you enable timestamps on them, you can see that things are happening in an order that's not as causal as it was before. Yeah, and of course then this means that timestamps can be out of order. So you can see that in the trace log you will have trace events where the timestamps jump up and down, but they are consistent within all of the different concurrent identities. Tracing to a port does not have this problem. So there's no ordering. Tracing to a port works as before. It's just tracing to processes that has this problem. But ports works as before, and therefore some small reordering may happen. So I did some benchmarks on this new system. So I have 10 processes doing 1250 ASON1 encodes per process. They generate about 7 million trace messages per run. So, and I measured time until the benchmark has completed. I measured time until all of the trace messages have been delivered to the recipient. And I measure the memory that's being used at the time. So as a baseline, running without any tracing, we can see that it scales with more cores. I use hyperthreads, so it doesn't scale anymore when I get over half of the cores. But you get nice scaling in the beginning of the first anyway, for these different processes running in parallel. And it takes about 25 microseconds per decode on this part, and then it takes about, 7 microseconds per decode here, as I add more schedulers. And another thing here is like, see, 19, faster than 18 off the bat. It's good stuff. Without any changes from my part, it's just the compiler and the virtual machine has gotten faster by 2-3%. It's cool. So tracing to a process, again, this is measuring completion time for the benchmark. So for running with one scheduler, the actual completion time went off the chart for 18, but with 19, we're running at about is it 300 microseconds? So it's about 10 times performance loss versus not tracing, which is not really great, but it's still better than 100 times performance loss. And we can see we have about the same curve in the different things, and it's about 3 times faster. So that's good. If we add how long time it takes for the trace to be delivered, we can see a similar pattern. So the rightmost here is how long it takes for the trace messages to actually arrive to the other side. So this is again tracing to a process. And this is off the chart, and then we see it's still faster, 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 and it's about the same difference in the different columns from when the trace messages, when the benchmark is being completed to when it's actually delivered the trace messages. Tracing, okay, so this is arity tracing. So the other one was tracing with all the function arguments. So this is tracing with arity, so without the functional arguments. And we can see that it's quicker, so it's about 200 microseconds instead of 400. So about twice as fast to generate with just arity. And the last one is even, it's getting closer to running without tracing. So actually having those arguments there adds a lot of overhead because you have to copy quite complicated structures in order to trace arguments. Tracing to a port, we have this nice thing saying that, okay, so with one scheduler, we are at about the same performance as in 18. But in 18, we have this beautiful curve going straight up here, saying that it gets slower to run the benchmark, and until the delivered trace messages are there, the more schedulers I add. So the more machine power I add behind it, the slower the actual problem takes to solve, which is not good. But in 19, we can see we have about the same performance gain here. So that's a great improvement. And tracing to port is basically tracing to file. So this is great for this. For this specific benchmark, I trace to dev null. So the disk isn't really an issue, but I just generate trace message as quickly as possible. And this is the lock, this system message dispatcher lock that was there to synchronize before. That's playing haywire with the results, which is not good, but this is good improvement. Let's see. Yeah, so this is for arity. For arity, we don't have the same steep curve, but we still have the same kind of general path saying that it gets slower and slower and slower the more schedulers we add. Memory usage, about half. So half the memory usage during the tracing. So far, only good stuff. And when you do it with arity, it's even less. So with here, I was using about 5 gigabytes of memory, and then it's about 1. So it's 1/5 of the memory that's being used during tracing. It's pretty nice. For port memory usage, we can actually see that 19 uses a lot more memory, but that's just because it has some inkling of speed, so it can actually build buffers. In the previous 4 ports running in the old one, it didn't have the momentum to build any kind of buffers, so everything was just synchronous, and it didn't have time to build any buffers, except for the first 2 here. We can see it builds some buffers, but here it just slows down to a halt the speed, and therefore it uses no memory, which is a good thing, but it's slow as hell, so not very good. So that was that about the performance things. Pretty nice. There's a couple of new features I want to talk about as well. That's there. Oh, I'm running out of time. Sorry. So tracer modules. I have to go quickly. We have tracer modules that allow you to hook in earlier to work with tracing as they are happening. So you can kind of, instead of a process or a port being called, you call a module that takes care of the event. You set it up. It's basically, you write a module like this, enabled, so if the trace is enabled or not, tracing, what to do with the trace. Unfortunately, in 19 now, they have to be NIFs, so they have to be implemented as native functions, all of them. We have written the new tracing implementations that you just saw are tracer NIFs. So they are written as tracer NIFs in these parts, and process and ports and dtrace system type LTTNG backends exist for it. Yeah, I want to add more stuff here. Some benchmarking to show the difference. So doing port to file or NIF to file here. So sending it to port that does to file is the leftmost one, and then just implementing a module here goes around saying that it's about, what is it, about 20 times faster implementing a tracer NIF than to do the one that was the quickest one that I had before. So we are using this, we can get another about 20 times improvement on tracing performance. Cool. We added more match specifications. You can now add match specifications on sending, so the event of sending a message. So we can do trace on other nodes only, or receive messages that are being done with GenCast, it's the first element. And we plan to add more of these in the future, or we do some other solution. We'll see. Also added port tracing events, so you can get events of what's happening with the port as it's being traced. So you can see when IO format writes to the file, hello world, we can see what the port receives, this command thing, and then it sends this as a return saying, it went okay. And then we close it, and we can introspect exactly what's happening with the port. This was not possible before to do with ports at all, so you couldn't trace that. So the future. So what we've done is that we've done more early filtering with Erlang tracer modules, match specifications, dtrace, LTTNG support. We've dealt with the overhead of performance, the scalability. We want to work more with doing overload protection and getting the throughput to be even better so that you can shove the data through. And then in the future, we want to work more with the different tools around these things, because now we're working with kind of the fundamentals of everything. That was that. Questions, please. Yes. So the first question is, the scaling, does it happen automatically? Yes, no change in the benchmark at all. So I'm running 10 processes on the 1 scheduler or 10 processes on the 8 scheduler problem. So it's the same problem that's being solved in the different parts. So it should be slower with 1 scheduler than it is with 8. And the other question was if I'm using any kind of message bus to do these kinds of events. No, that would be a great example of how to write your own Erlang tracing NIF backend for doing that kind of thing.
All right, thanks.
Any other questions? Eric, there and there. Okay. Dima?
So that meta tracing mode, is it happening implicitly at some point, or do you have to explicitly say meta in your tracing call?
You have to say, when you set up the trace pattern, you have to explicitly say that this is a meta tracing point that you're working with.
So it cannot happen as a surprise to me. So
No.
like
No, you have to explicitly tell the thing that it's working there. Yeah.
We have a question here.
No, I think they retracted. They didn't want to do. All right. Yeah. One more. Yep.
So this basically how this global variable affects on performance when say it disabled. Does it run faster when say you set this variable to be disabled?
Yes, I mean, so the match specification. So the question is this trace control word that you can set as a global trace variable that you can drive behavior on. How does it affect performance? So the match specification engine is run very, very early in the event loop of a trace message. So it has to run that specific match specification, but when that is done, it bails out very, very quickly. So it just reads that variable and checks out, okay, so is it the same, and then returns. So using that has, I don't know the overhead percentages, but it should be around 50–75% overhead just bailing out like that.
So it's basically kind of safe to have the tracing patterns on your production system and being disabled by default. and it won't affect the performance.
It will affect. It will. How much depends, as always. What you do, I can't. I've measured this, but I can't remember the numbers. I'm sorry. But if you just set it up and do some kind of easy tracing, should be I don't know, 30, 40, 50% overhead per function call. So it's kind of, and if you will see that or not on your system, I don't know. It depends.
Okay, thanks.
How this sequence tracing works? I mean, if there is a sequence of messages, all of them will be traced, or I'll get one final message that says that this sequence was executed.
Sequence tracing works by saying that, okay, so I can say the next message that arrives to me, I want to start a sequence trace, and then embedded kind of in the metadata of all the next message that process sends, a token will be sent forward and enabling sequence tracing on the next process and so on. So it's I don't know the documentation exactly and how it works by heart, but it's something like that. So you enable it for the next thing that's coming, and then you trace for that event. Or you can set up some kind of match specification that says that, okay, so when this happens, then I want to enable sequence tracing on this process that's in there. So you have different ways of setting it up in there.
You have time for one last question? Oh, let's thank the speaker then.
Thank you.